So this experiment is called LDR Characteristics. We are trying to see how a light-dependent resistor behaves when we, expose it to light. How the resistance changes. This experiment is an analysis of that. So basically, what we'll do is we have the setup. In the setup, there are two circuits. You can see there are two circuits. This circuit is for our source, light source, and it's completely an AC circuit, right? And the other circuit is the one where you connect your LDR, the light dependent resistor. So this here is the light dependent resistor. If you see inside, this is a semiconducting device. So this is a light sensitive resistor. So the resistance of this device changes as the brightness of surroundings changes. So what we're doing right here is we have a bulb and we are changing its brightness. We have a LDR here and we are seeing how the resistance of this LDR, how the resistance changes with respect to the brightness of this bulb here. Okay. You have your source here. You have one voltmeter and one ammeter kept near the source. And on the other side, you have your power supply. Okay, power supply for your LDR. And you keep your power supply, you have a milliammeter and a voltmeter. So one thing that you have to note is there are two kinds of milliammeter. Okay, they differ in their ranges. So this milliammeter has a range up to 20 milliammeters, and this one has a range of 2000 milliammeters. Since this is like live current, so we need a ammeter of a higher range. So what you do is we need to measure the current that this bulb is receiving and the voltage this bulb is receiving. Right? How do we do that? You just randomly connect these two where 320 volts written. You connect it across your voltmeter. Okay. And you connect this across your ammeter. And will polarity matter here? Polarity won't matter because it's a AC circuit, right? In AC circuit, polarity is constantly changing, so it doesn't matter. So what we do is you connect your ammeter, the ammeter with a higher range, and you connect your voltmeter. So once you connect this, when you turn on your voltmeter, you have to make sure that you go towards AC. And what is the voltage that you're measuring? You're measuring 230 volts, right? So its range has to be in 200s. Okay. So what we'll do is we have a potentiometer here, and potentiometer is basically a resistance that can vary. Basically, when I turn this knob, the resistance varies. So basically, what happens is the voltage across this bulb changes when I change this knob. Basically, that's why you can see the brightness changing. So the peak value of the voltage here is 230. It can't exceed 230 because that's the source we are getting. So since the resistance is high, so you'll get something that's below 200. So you keep the range around 200. And one more important thing to mention is I said that this is a potentiometer, but in the circuit it's given as a rheostat. Right? A rheostat and a potentiometer's function is exactly the same thing. That is, we want the resistance to change when we do something. Right? Here basically I'm turning the knob. In rheostat I move the slider. That's all. That's the only difference. Now, one very important thing is, since this is live AC, once you connect this circuit properly, you're not going to touch it. Right? If you touch it, what will happen? You will get thrown out of the lab by the current, not by teachers. Okay, now we just got on with this part of the circuit. Now we are trying to connect this part. Now, this is the LDR that's connected here. Now, as you can see, LDR's negative is connect. What we'll do is we'll first finish this, then we'll connect the voltmeter across the LDR. Okay. Now the LDR's negative, right? Here polarity matters because this is a DC circuit. The negative of the LDR is connected to positive of milliammeter. Positive of milliammeter. And the negative of milliammeter is connected to the negative of your source. My source's negative is the one that's in black Latin color. Yeah, now positive of the source is connected to the positive of LDR. Positive of LDR connected to the positive of the source. Now this part of the circuit is over. Now what do I want? I want to measure the potential across the LDR. So what will you do? I will connect this voltmeter across LDR. Positive, positive, negative, negative. That's very important. Right? Otherwise you will get negative voltage. Positive is this. I will connect it to the positive. And the negative of the LDR. To connect it to the negative of voltmeter. Okay, negative of LDR is here. And it's very important that you connect the voltmeter across the LDR, not across your source. Then it won't make any sense, right? Here already they're showing what is the voltage across your source. What we need is voltage across the LDR. So why do you think the voltage across the source and voltage across the LDR will differ? If you can see here, I have a milliammeter, right? So there will be some potential drop across this milliammeter. So we want to account for even that change, right? Because we want the voltage across the LDR and current passing through the LDR. Okay, that's what we are measuring. This is a DC circuit. So this has to be DC, right? Now, what should be your rating here? Like, what should you choose, right? Should you choose 220? If you see in the book, it's written that we take 4 volts as a voltage, right? So we can keep it at 20. 2 will be too less and 200 will be too much. So your accuracy will reduce. That's why we need to have the range as 20. Okay. Here the range will be 200 AC. So one important thing before you start the experiment is you have to make sure that the distance between the bulb and the LDR is somewhere around above 30 centimeters, right? So take a scale and roughly keep it above 30 centimeters. You see, it's obviously around 40 centimeters. So this is the ideal distance. Now, before we start doing the experiment, we have to make sure that the voltage here is around 4 volts, right? Like there is no rule that it has to be 4. You can keep any one constant voltage, but for uniformity, let's keep it at 4 volts. When we keep the source at 4 volts, you can see that here we have around 3.85. Why is that? Because there is some potential drop across the ammeters. Okay. Now what we do is switch it on and keep it at the lowest setting, and you vary the voltage. You vary this voltage across the bulb in 10 voltage gradations. Okay. So you start with around, let's say 90. Here 90 is, for some reason it's not possible. Let's say you start at 90, you go till 200. Okay, 90, 100, 110, you go till 200. So when you change this, this is what you'll be changing. You will measure everything else with respect to this. Okay, so that's what you've done here. 80, 100, 120. Actually, what you do is we need more number of points because it happens so that it's a exponential decaying curve. So for that, we'll need a lot of points. So we'll start from 80, 90, 100. We'll go till 200. Okay. So as you see, when I'm changing this potential, this regulator, let's call it regulator. When I'm changing the regulator, the brightness is increasing. Why is that increasing? Because the voltage is also increasing. You go till around 160, 170, around 200. Go till 200. Okay. So since we have kept this at 200, we can measure only till 200. Right? You can't go above 200. See, if you go above 200, you'll get like this. Okay. So we measure from 90 to 200, and you measure all the other with respect to that. Okay. So this is voltage across the bulb, current passing through the bulb, voltage across the LDR, current passing through the LDR. These are the 4 columns. Voltage across the bulb, current passing through the bulb, voltage across LDR, current passing through LDR. So this is voltage, current. This is for bulb, this is for LDR. Okay, this is the first part of the experiment. So now what we need is we have the voltage, current across the bulb. So what we know that when you multiply voltage into current, you'll get power. So we are passing that the power output of the bulb, right? That's what we are calculating here. And again here we have the voltage across the LDR, and you have current passing through the LDR. So when you divide voltage by current, what will you get? You get resistance, right? So we are measuring the light output, in terms of power, and we are measuring the resistance across this. Okay. So for this you multiply both, for this you divide V by I. So once you get all these readings, what you do is you plot power across resistance. You will get this graph. How do you plot a graph? This along x-axis, this along y-axis. Now next part of the experiment is to prove that the thing that's actually changing with respect to light is the resistor. Okay. There are a lot of components in the circuit. We don't know what's reacting to the light. So we have to prove that it's a resistor. Now what we'll do is we'll keep the power constant. Okay. We'll keep the brightness of the light constant. How do we do that? Switch it on. At some voltage, let's say 150 volts, we keep it constant at 150 volts. We are not going to change this. We are not going to touch any of that. Only thing what we are going to do is we are going to change the voltage, okay, and we are going to measure what the current is. When we change the voltage here, right, we don't take this reading. We take voltage across the resistor. I'll start with 3 volts. But the thing is, I have to make sure that it has 3 volts here. Now, I take this voltage and I measure what the current is across. Like I just take readings. Okay. Now, what's happening here is, since the brightness is constant, the resistance will not change. Okay. So that's what we have to prove. When I'm changing for different voltages, I have different potential across the resistors. So I measure different potential across resistors 3, 4, 5. I change this potential in degrees of 1, right? And I get the current. What I see is, if I plot a graph of voltage across resistance, I'll get a straight line. Why will I get a straight line? Because resistance is constant. Okay? Resistor is a ohmic device. If I don't change the power, then the resistance won't change. I'll get a straight line. Okay, so that's the experiment. You'll have to draw 2 graphs. One is power across resistance. One is voltage across current. Now, once you're done with all that, you have 2 graphs, right? So one graph where I've kept the voltage across the bulb at 150, and I've measured what the resistance is, right? How will I measure the resistance? I'll take the slope. The slope will be nothing but the resistance, right? Now I'll calculate this resistance. That's one of my reading. Okay, that's one of my result. The other result is in this graph at 150 volts, and whatever power, right? Whatever power I have at 150, I have this much power. Okay. So at this power, I'll draw a straight line parallel to y-axis. We'll cut the graph at some point, and at that point, I'll draw a line parallel to x-axis. It'll cut at some point here, and that is my resistance. Now, since the voltage is 150, I got some resistance. It has to match with whatever resistance I get here. Like it's the exact same setup. The resistance should not change. So both values you have to get approximately the same. So that's the experiment.